In section 1.5, we look at some other things we can do with trigonometric identities. So in the first example, we are asked to write tangent of theta in terms of sine of theta. So to do this, first let's just remember that we know that tangent of theta is equal to sine of theta divided by cosine of theta. And the reason I'm choosing this identity is because at least this brings into the problem a sine of theta, which is what we are tasked with doing, right? They're telling us to do this in terms of sine of theta. The problem is we have the cosine of theta down here. So how can we write cosine of theta in terms of sine of theta? Well, we know that cosine of theta is equal to plus or minus the square root of 1 minus sine squared of theta. This was one of our identities from the last section. And so in the end here, we can rewrite this as plus or minus with a fraction bar sine of theta over the square root of 1 minus sine squared of theta. And notice now that we have expressed the tangent function in terms of the sine function alone. Now also keep in mind that plus or minus here does not actually mean positive or negative. The plus or minus is dependent on the quadrant, right? So we need to remember that this depends on the quadrant, right? So for example, if we know that we are in quadrant 3, we know that tangent is positive in quadrant 3, therefore we would pick the positive sign. However, if we knew that theta was in quadrant 2, then in quadrant 2, tangent is negative, and we would pick the negative sign, right? So we would need more information to evaluate this. If we were actually trying to plug in values, we would have to know some information about the quadrant in order to know whether to pick positive or negative. In the second example, we are asked to write secant of theta times tangent of theta in terms of sine theta and cosine theta, and then simplify. So secant theta times tangent of theta, we can write this in terms of sine and cosine by using the reciprocal and ratio identities. So we know that secant of theta is 1 over cosine of theta. And we know that tangent of theta is sine of theta over cosine of theta. And so if we multiply these together, 1 times sine of theta is sine of theta, and cosine of theta times cosine of theta is cosine squared of theta. So we end up getting sine of theta over cosine squared of theta. Now it then says, and then simplify. But really, this is as simplified as we can make this, right? Now, I do want to point out that if they were to ask us to write this in terms of, let's say, sine of theta alone, then we could take an additional step here, and we could say that this is sine of theta over, and then remember, cosine squared is the same as 1 minus sine squared, right? So this would be an alternative answer had they asked us to write it in terms of sine of theta alone. But the fact that they asked us to write it in terms of sine and cosine means that this answer here is perfectly fine. The main thing to keep in mind is that there are different things you can do with these expressions using various trig identities. In the third example, we're being asked to add 1 over sine of theta and 1 over cosine of theta. So the key concept here is that you can only add fractions when they have a common denominator. The least common denominator between sine theta and cosine of theta is sine of theta times cosine of theta. So what I can do here is I can multiply this first fraction by cosine of theta over cosine of theta, and I can multiply the second fraction by sine of theta over sine of theta. And when we do this multiplication here, cosine of theta times 1 is cosine of theta. cosine of theta times sine of theta is basically cosine times sine, but I prefer to write this as sine times cosine. Plus, and then for the second fraction, we can multiply here. 1 times sine of theta is sine of theta. And once again, in the denominator, we have cosine of theta times sine of theta, which I'm going to write as sine theta cosine theta. Now that we have a common denominator, we can add these fractions together. That common denominator will be the denominator of the answer. And then all we need to do is add the numerators. And so that's going to give us cosine of theta plus sine of theta over sine of theta times cosine of theta. And this is our answer. Now, I want to warn you of something that I see quite often. So a very common mistake that I will see when students get an answer like this is they will try to simplify this answer, and usually it will go something like this. They will say, well, we can cancel a cosine here, and we can cancel a sine here. And then they end up getting an answer like 1 plus 1 is 2, right? And that's just not true, okay? And the reason that's not true is because you can only cancel factors. You cannot cancel terms. So what I mean is you can only cancel things that are multiplied and divided. You cannot cancel things that are added and subtracted. So, for example, just to make sure we really understand the point, if you had something like 3 sine of theta times cosine of theta divided by sine of theta times cosine of theta, because this is all multiplication here and this is all multiplication here, we would be able to cancel the sine and also cancel the cosine, and this would indeed be equal to 3, okay? However, for this one right here, this is not true, okay? So this is complete nonsense, all right? So we have to make sure that when we're simplifying expressions, we know when to stop. We have to know when we have our final answer and when we cannot simplify any further. In the next example, we're asked to multiply a couple of binomial expressions here. And what we have, of course, is sine of theta plus 2 multiplied by sine of theta minus 5. And so this should take you back to a procedure that you dealt with in algebra called FOIL. And of course, what that means is we are going to multiply the first terms together. That's the F. Then we are going to multiply the outside terms together. That's the O. And then we multiply the inside terms together. That is the I. And finally, we multiply the last terms together, and that's the L. So when we go through this procedure, we get sine of theta times sine of theta, which is sine of theta squared. And then when we multiply the outside terms, we have sine of theta multiplied by negative 5, and that is quite simply negative 5 sine of theta. And then positive 2 multiplied by sine of theta is positive 2 sine of theta. And finally, positive 2 times negative 5 is negative 10. And there's just a couple of things left to do here to simplify. First of all, sine of theta quantity squared, we want to use the convenient notation of expressing this as sine squared theta. And also, negative 5 sine of theta plus 2 sine of theta can be combined together because they are like terms, and we should have negative 3 sine of theta. And then finally, the minus 10 at the end. So this is just like multiplying out binomials in algebra, except that now instead of having just a variable, you have a trig function taking the place of your variable. The next example is a review example from algebra. We are asked to factor the expression 9 minus x squared. So I just want to remind you that when you factor something like a squared minus b squared, you might remember that this is what we call the difference of two squares, and the difference of two squares can be factored into a minus b times a plus b. So when you have something like 9 minus x squared, think of this as 3 squared minus x squared. And when I go to factor that, to get 3 squared, we're going to have 3 times 3. And to get x squared, we'll have x times x. And the negative here means that we have to have one negative and one positive in order to get negative x squared. And so this is our answer. And of course, you can check your work. You can do the FOIL procedure. 3 times 3 is 9. 3 times positive x is positive 3x. Negative x times 3 is negative 3x. And negative x times positive x is negative x squared. And these terms cancel out, and we end up getting 9 minus x squared, right? And so that checks out because we get what we had to start with. Now, the whole reason I bring up this example is to talk about the next example. Factoring 9 minus sine squared is exactly like factoring 9 minus x squared. So when you have 9 minus sine squared of theta, you want to think of this as 3 squared minus sine of theta squared. And then when we go to do the factorization, it's exactly like what we did up above, except that instead of having an x squared here, we have a sine of theta instead. And so on our answer, instead of having an x here, we will have a sine of theta. So we get 3 minus sine of theta multiplied by 3 plus sine of theta. So all the factoring that you've done in algebra is going to be a factor, no pun intended, in this class, right? In other words, later on in the course, we will be solving equations, and we'll need to know how to factor in order to be able to solve those equations, just like you did in algebra. All right, in the next example, we want to show that the following statement is true by transforming the left side into the right side. So oftentimes what you'll be asked to do is prove the following statement. Now, when you do a proof, what we're going to do is we're going to write down what we want to prove, which is this statement. And then what I like to do, at least in the beginning, is I like to draw a vertical line right below the equal sign. And then what I'm going to do using identities is I'm going to take the left-hand side and I'm going to try to transform it into the right-hand side by using basic identities. So for example, in this problem, when I start here, I have cosine of theta. And cosine of theta is pretty basic, so I'm going to leave that alone. But tangent of theta, remember, has a ratio identity. So we can convert this into cosine of theta multiplied by, and then tangent of theta is sine of theta over cosine of theta. Again, we just use the ratio identity for tangent. Now you can see what happens when you multiply here, right? So if you want, you can put an over 1 right there. You can cross-cancel the cosine of theta, and what you end up with is sine of theta over 1. And of course, sine of theta divided by 1 is sine of theta. And so now you can see what we have on the left-hand side matches up perfectly with what we have on the right-hand side. And so we have proven that this expression here is the same as sine of theta, with the one little proviso that theta can only be a value for which the functions are defined. Okay, so this is true if theta is a value for which each expression on the left and right are defined. Now, what exactly does that mean, and is this such a big deal? Well, it's not really that big of a deal. You don't really have to think about this consciously. But let me just give you a quick example. If theta is equal to 90 degrees, tangent of 90 degrees is undefined. Okay? So since tangent is undefined, that means the whole left-hand side of the equation would be undefined if theta was 90 degrees. So this is not true if theta equals 90 degrees. Okay? And it's also not going to be true at any other value of theta for which tangent is undefined. Now, we don't have to spend a lot of time thinking about that right now, but just know that when you're proving an identity, you are assuming that you are proving this is true as long as the expressions on both sides of the equal sign are defined. Okay? So just keep that in mind. In the next example, we would like to, once again, do a proof. We want to prove that sine of theta plus cosine of theta quantity squared is equal to 1 plus 2 times sine of theta times cosine of theta. And to do this, I'm going to draw a vertical line again. And I'm going to pick a side. I'm going to start on the left-hand side and show that it is equal to the right-hand side. And the reason I'm picking the left-hand side is because there's something for me to do here, right? So they're telling us to take sine theta plus cosine of theta and square it. So what does it mean to square something? Well, it means to multiply it by itself, right? So we can do this. And then from there, we can FOIL, as we talked about earlier. And when we do this FOIL process, we get sine of theta times sine of theta, which is sine squared of theta, plus sine of theta times cosine of theta is sine of theta times cosine of theta, plus, then we have cosine of theta times sine of theta, which is sine theta cosine theta, plus, and then finally we have cosine of theta times cosine of theta, which is cosine squared theta. So what I have here is sine squared of theta, and then notice that we have plus 1 sine theta cosine theta plus 1 sine theta cosine theta. That's going to be 2 sine theta cosine theta, because those are like terms, plus, and then we still have cosine squared of theta. Now, because of the commutative and associative properties, when I add these together, I don't have to add them in the order that they currently are listed in. I can take sine squared and add it to cosine squared. And we know that sine squared plus cosine squared is equal to 1, because that is a Pythagorean identity. And so when I replace sine squared plus cosine squared with 1, we end up having 1 plus 2 sine theta cosine theta. And then at that point, I'll just point out that that is the same as what we had on the right-hand side. And so we have proven that these two things are equal. In our last example, we want to simplify the expression square root of x squared plus 4 as much as possible after substituting 2 tangent of theta for x. And for this problem, we are going to assume that theta is between 0 degrees and 90 degrees. All right, so I just want to point out a really basic thing about radicals. And the basic thing is that when you're taking the square root of the sum of two things, this is not equal to the square root of the first thing plus the square root of the second thing. It sure would be nice if this were true, because then you might be able to think of this as being x plus 2, but you cannot do this, okay? So this is just rubbish. So what we're going to do is take the advice given, which they said, substitute 2 tangent of theta for x. So what that means is we're going to let x be equal to 2 tangent of theta. And what we have is the square root of x squared plus 4. So because x equals 2 tangent of theta, we are going to substitute 2 tangent of theta in for x. When we do that, we get the square root of x squared, which becomes 2 tangent of theta quantity squared plus 4. Now let's see what we can do with this. Squaring 2 tangent of theta, you can square the 2 and square the tangent because this is multiplication. So squaring the 2, you get 4. And squaring the tangent, you get tangent squared. So this is kind of nice because you can see that we have a common factor of 4 right here. So now that 4 can be factored out within the radical. So when we pull out the 4, what we have left over is tangent squared of theta plus 1. And this is where the magic occurs. Tangent squared of theta plus 1 is secant squared of theta, right? That's an identity. So we can replace tangent squared of theta plus 1 with secant squared of theta. And then finally now we can rewrite this as the square root of 4 times the square root of secant squared. Because when you have a radical, as long as the things are being multiplied, you can separate the radical like we've done here. Now once we do that, the square root of 4 is 2, and the square root of secant squared is technically the absolute value of secant. However, because we are under the assumption that theta is between 0 and 90 degrees, that means that theta is in the first quadrant. And in the first quadrant, secant is already positive. And so what that means is that these absolute value bars right here, in this case, they are unnecessary. So we can remove them, and this is the answer that we get. So what you've seen in this section is that we can use various trigonometric identities to either simplify expressions, to prove other identities, or to use these algebraic substitutions like we did here to simplify an expression in a different way.